here's an example where we have at Stanford radiology. They basically ingested PET-CT images. I think actually it was a lot lower than 500. It was something like 289 or something. And they managed to get the paper published at the RSNA, which is one of the top radiology conferences in the world. And they basically used a method in machine learning called ensemble learning to be able to build a fairly accurate model that was about 75 or 76% accurate, which you consider like 289 data samples, which includes both validation and training. It's actually a pretty small data set, but they're still able to get some good results from that. So this would be how you would use it. So this is an example of very simple image analysis. So we have two cases without pathology or with pathology. My wife is a radiologist, and so when I put tumor versus no tumor, my wife was not very happy with that because she said, no, an AI determines pathology, not whether there's a tumor or not. It's just whether something's suspicious. So I modified that. So without pathology, it's 0. With pathology, it's 1. And so essentially you have a bunch of images. The only thing you need to do is put the images in the right location, and NeoPulse will ingest that and train the model. So the CSV file is simply, you have a label, path, 0 for without, 1 for with. So this is NML. So basically NML will allow you in just 14 lines of code to build a full classification model. And so obviously this is a lot less code than you normally would write to do machine learning. And so as you can understand, this is one of the reasons why I often use, I wish this were around like 5 years ago when I was doing a ton of machine learning for Intel, because it could have saved me months of work. So I think that this is something that, yeah, it's relatively straightforward. So the first thing is you say that it's a classification problem. That's what the Oracle mode is. So there are many hints you can provide to the Oracle. So whenever you see Oracle with something in quotation marks, it's a hint that you're providing to the Oracle. You're basically letting the Oracle know how to think about the problem. So the next line is the source, in which case you're just specifying where the .csv file is. Right now we only support .csv files. Later on we do plan to support other data types as well, like ODBC types of connections and so on. The input is from path, and so it's an image. So this is why we have an image data generator. So image data generator, or we have this idea of data generators inside NML. So data generators are things which completely structure the ingestion of data. So when you think about it, just think about what that one line does. It's taking the path to the source. It's resizing it to a 28 by 28 image. It rescales the image to, so that weird number is simply 1 over 256. So it rescales it to a value between 0 and 1. It does all of these things in one line. So basically ingesting the data in an efficient way, loading it up into memory, resizing it, rescaling it. You can do all kinds of other things like you can do a lot of data augmentation. So for example, you can change you can change the orientation, you can change the rotation, you can do all kinds of things like that to increase the variation in the data. So if you have a more limited data set, you can grow the data set a little bit by using data augmentation. Label, you see 2. So that basically means that we have just a vector of, so flat is basically, a flat data generator is a simple vector. And in this case, it's got 2 dimensions, 0 for without, 1 for with. And batch size 32, so batch size basically, if you have a beefy machine, you can set the batch size to 1024 or whatever. If you have a small machine, probably even less than 32. And we have something called number validation, which is the number of data points to reserve for validating your model. But you can also do proportionate too. So you can actually specify 20%. So you can write validation 0 equal. So there's I'll show you an example where you specify a percentage, not the actual number. Everything happens under architecture. So this one line, X to auto to Y, will build your entire model for you. So when the compiler sees auto, what it'll do is it tells the compiler to go to the Oracle for help. And wherever it sees auto, it is context aware. So in this case, it understands that it needs to work on the full architecture, but it can also help you with parameters or functions or anything else. And even distributions. So for example, you can say, hey, help me within this range. Can you pick out a value for me? So auto basically once the compiler sees auto, it goes to the Oracle. The Oracle will construct your entire model for you, figure out the best architecture, determine what the best set of hyperparameters are for that problem. Will also take care of any other types of optimizations that are needed. Typically, I mean, that can be pretty hairy in terms of if you want to write out that and figure that out, that in itself takes a long time. It takes the Oracle maybe a second to generate about 4 different model architectures and associated hyperparameters. For human, that would take you much longer. You're talking about maybe weeks, days to weeks, depending upon how good you are. And the thing is, by doing that, this gives you the flexibility of knowing, fail fast, so you know whether your models really has any predictive value or not, based on because it can compile and build models so quickly. And then finally, if you don't know what an optimizer function is, you don't know what a loss function is, you can set that to auto as well. And the last part is metrics equals accuracy, saying that I want to optimize my models for accuracy. You can also optimize for loss, and very soon you can also optimize for machine architecture. So for example, if you have limited memory, your target machine has limited memory or limited processing power, you can also set metrics to optimize for that. And so what it'll do is it'll essentially solve an optimization problem, saying, okay, based on the amount of memory that you're giving me, the amount of processing power you're giving me, and that I have to optimize for accuracy, this is the most optimal, accurate model I can give you with those constraints. So it basically allows you to give constraints to the actual AI model, so that when you actually deploy it, you can deploy it onto a target. And epochs is basically the number of iterations through your model. So as I said, you submit the NML to, and you're not technically submitting the lung.csv. Everything is contained in the NML file, but you're ingesting the data. There are basically as I said, about 700,000 different algorithms to pick from. So it'll try and determine what is the best algorithm for your problem. And that list of algorithms is growing. We are developing a way right now to, essentially, as I said, we're looking at reinforcement learning to train so that AI Studio will learn from previous mistakes and will continually improve. So it'll continue to modify the machine architecture, the actual machine learning architecture and things like that. So it's basically grows its vocabulary in terms of what it can solve. We offer a queuing model for AI Studio, which basically means that once you submit your model, you can immediately start working on the next one. So we have both AI Studio as well as NML work on a queuing principle. The reason for this is because we want to ensure that it's you can always guarantee you're getting a response for for example, you're talking about the runtime. We want to make sure that anytime you submit a request, we don't want that request to be ignored by the machine. So as soon as you submit a request, it gets put into a queue to solve, to interrogate the model. And so the queuing model offers several things. One is it gives you work asynchronously. You can submit when and where and when you want, so you don't need to worry about the machine being occupied or not. It's really entirely dependent upon the capacity of the machine, how many items you can have in the queue. You can add as many as you want, and then it'll kind of just go ahead and solve that. We give you multiple ways to evaluate. So for example, you can look at accuracy, validation loss. You can actually see the underlying architecture in this case. For example, this is actually not a vision problem, but you can determine kind of what the back propagation paths and everything like that. It's sitting underneath the hood is TensorFlow, so which means that you can exploit all of the advantages of TensorFlow, including using TensorBoard with this. And we also give you information about whether or not it can run in TPM. So how TPM compatible is the underlying model that you have. You can also see hyperparameter choices. So it's hard to see, but you can see the loss function, the optimizer function here. You can see the activation function we use, and different types of layer depths and so on that are associated with that. So it gives you sort of an overall view of what was built. So it's not just simply, hey, here's a PIM. We give you a ton of information about it, like the architecture, the hyperparameters used, the like the validation data and stuff like that. And so very soon, this list is going to include a lot more stuff, like for example, sensitivity, specificity data, F-score, ROC curve. We'll also be looking at histogram, like a weights histogram and things like that for people who know what they're doing. So that also gives you a lot of opportunity there to evaluate the models. So once you're satisfied with your PIM, you export it, and it literally is just one file. It's a .pim object, which contains everything. And that contains the model, it contains the metadata, it contains like optimization instructions. It actually contains there's a lot of stuff. So it basically when you finally execute it, you put it on the machine, the runtime will determine what it needs from the .pim object for it to run in that particular environment. You can customize the .pim. So in probably not in the next version, but the version after, you can actually set controls on your .pim object so that so for example, so you can have a debug version of your .pim object, which you distribute to your team, which will include information about the underlying machine architecture and so on. But if, for example, you have proprietary data, you don't want to reveal what you did, you can actually stop that. You can prevent that from going out. And then finally, it generates an API automatically that your application can call. So in terms of how it can be used, so suppose you have a simple user interface and an application. So you submit the, in this case, an X-ray to your application. The application makes a REST call with the image to the runtime, which is hosting the .pim object. The .pim object returns no pathology present in this case, or returns pathology with a certain probability. So again, it determines, part of it is determining what is the best loss function to use. So if used, for example, categorical cross entropy or binary cross entropy, you can have different, if for example, it could be, maybe it's multiple, it's possible for it to fall into multiple categories, or maybe it's just only one or the other. So for example, binary cross entropy would be, it's definitely either in one category or in another. So AI Studio, when you have the Oracle will actually determine what is the best loss function for that. So if it sees that there's no overlap between these different objects, so in other words, the data does not fall into multiple buckets, the Oracle will automatically say, binary cross entropy is perfect for this, or categorical cross entropy is better for this. For regression, it'll kind of say, you know what, I'm going to use a mean absolute error or whatever. So it'll make decisions based on the kind of data that you're working with. So all of those decisions are made for you. So one of the problems we worked on, and this is just because I talked about a classification model. This is a the volatility index. So the S&P 500 has like an implied volatility. Volatility in this case is how much fluctuation exists within that market. People call it the fear index, because when you see high volatility in the market, that's usually not a good sign. Right now, you're seeing tremendous volatility in the market. I have never seen that much volatility before. That was like the last time I saw this was 2008. That was kind of, which is not a very good indication of where our economy is going actually right now. But anyway, I'm digressing there. But the overall thing is that, so when you look at volatility, you can actually see, I like this problem. So, so my first job straight out of college, I was, because I did a theoretical physics degree, I was working as a quant, for a short period of time. Which is a quantitative developer. And so, which is finance. And ever since then, I've just loved financial problems. And so this is why. So the early 90s, there was a recession around 1991, and you could see that the volatility spiked. From basically 1998 to 2003, you see the volatility changed quite substantially again. The volatility in this period, can anyone tell me what was going on in between 1999 and 2003? .com, yeah, and 9/11 too, the two together, yeah. So yeah, and you see like right around 2001, you see things becoming unstable. Things were beginning to drop down, but you know, .com and 9/11 together was a very bad combination. Things started to get better, volatility dropped, and then around 2007, volatility increased again, and this was of course the big the Lehman Brothers collapse in 2008. This was that kind of happened there. Then that led to led to a lot of instability in the economy. Things started to get better, and I don't know what happened in 2015, but anyway. And then 2018, well, a certain president was elected, and every time he produces a new tweet, that results in some action in the marketplace. So the question is, given that, can you take the last 5 days and predict the next 5 days within that? So there's a lot of stuff I'm not talking about here, but one of these is this a solvable problem? And it turns out it is a solvable problem. And the reason for that, so when you look at the stock market is what's known as a Gaussian random walk, which is Gaussian distributed random walk, which basically means you will never ever get a signal that is not. So once you actually make it, so it's a non-stationary system, but if you make it so, which means it's growing over time, but once you remove that growth factor from the market, it becomes unpredictable, which the only thing you can say with the stock market is that over a very long period of time, it'll grow. That's all. But over a short period of time, there's no predictive value, and you can't predict anything, and you can prove that. So with the volatility index, it does not follow that. It is not a Gaussian distributed random walk. It actually has a certain method. So there's a certain structure involved. And so in this case, I gave a talk in London. It was at a financial conference. And so literally it took me 2 nights before the conference to actually build a model. This was actually with one London-based hedge fund. And so basically you've got X to auto to Y. So nothing's different. The only thing you'll notice is that I'm setting a regression value, setting it to regression and complexity. So what does complexity mean? So complexity is a measure of algorithmic complexity. So you can either choose very simple algorithms or very complex algorithms. There are some other tweaks you can make to the model. So you can, for example, Yeah, I'll talk about that later. But in this case, so one of the things, by the way, you notice that before I had source first and then I had architecture. So AI Studio doesn't care about the order. So each of these blocks is independent. So in this case, I specify the architecture next to auto to Y. I tried doing it myself and I never could beat the Oracle. So I decided to screw it, just use auto. But auto is consistently, using auto is consistently able to beat me. So I thought I'll just use that. It's a good demonstration of our capabilities. So then, you bind it to the training data. The previous is the previous 5 days. So it's a 5-dimensional vector. And you're predicting the next 5 days, which is another 5-dimensional vector. And specify batch size. Shuffle equals true means that I shuffle the data, randomize the data set before I actually put it in. Why is that? Why is it that I can do that in this case? Because isn't this a time series analysis? Why can I shuffle data? Exactly. You're just looking at 5-day to 5-day intervals. So, and this also says that every time so this says like init equals true. So which basically this says I'm going to shuffle the data before I start training. And then shuffle equals true means that I will shuffle the data between epochs. So if there is any bias built into the order of the data, this eliminates that. Number validation, which means I reserve 300 data points for validating my model. So in this case, same thing, but in this case, I set the metrics equals to .mae. So what that means is that I'm optimizing for mean absolute error for this particular problem. So it's pretty good. So in terms of the previous 5 days, this is the data. So it's basically hovering around 13, between 12 to 14. In the next 5 days, it was between 11.3 to 11.56. So it's kind of like low teens for the most part in this particular segment. So if you actually look at as the model trains, so every time, so these are at the bottom, on the horizontal are the number of epochs. An epoch is the amount of times, every time I put my data through my model, that's considered an epoch. So what you should see is that over time, you'll settle down to this really nice curve because, as you increase the epochs, it should stabilize onto at a certain value. And in this case, with the MAE turned out to be around 1.4. And you can basically check 1.4 against sort of the values here. So actually multiply this by the square root of 5, but anyway. And then compare the two, and then it turns out to be around 95% accurate. So which means that, with this model, I can actually predict the next 5 days with about a 95% accuracy. So here's an example. So with the model, so what I did was I trained the model for data up to about July of 2017. And then I wanted to test it against real world data. So I actually looked at volatility from 2017 to 2018. So this was basically this is just the standard VIX market. So the blue line indicates what the model predicted. And the red line or orange line predicts what the market or shows you what the market actually was. So, you can see that it didn't do that well around here, although it did predict that there's an upward swing. It got it wrong by quite a bit. So it was about value of 35, but 30, sort of 20. So it was off by around 20. But it wasn't too bad overall, but it did actually it was able to reasonably predict what the market was over this period of time. So, so as a result of that, so you can actually see that what the model predicted versus what the market was actually pretty accurate. Now, whether or not you could make money on this is a different question. So, there is actually a way. So there's something if you go down here. So, so to trade VIX so basically there are these things called ETNs, so exchange traded notes, and Uh, there's also an example of that would be, or another thing would be exchange traded funds. And it turns out that they have value. So basically, so when you have an exchange traded fund, these are basically a fund that is put like, you know what a fund is, like it's a combination of different assets. And so you can combine them and you can actually sell that combined set of assets as a single entity, and that has a certain value. And it turns out that that value, you can actually leverage that to make money. So if you know the volatility.